I'd like to introduce Paul Ivanov. He'll be presenting the portrait of the graduate student as a young scientist. Did I have that? A portrait of one scientist as a graduate student. And I tried desperately over lunch break to come up with some sort of James Joyce reference that would be funny. But instead, I was distracted, reminded that I've only seen to the end of season 2 of Breaking Bad. So anyway, Paul, please take it away.
Thank you. OK, let me start that timer that I promised. OK, hey guys. So thank you so much for having me, and thank you for being patient. Let me get rid of this guy. So what I'm going to talk about today is a bunch of sort of vignettes and tools, and I'm not gonna tell you how to mesh them together. I just want people to know about these. Some of them are gonna seem trivial to you. Others are maybe very esoteric, but nevertheless, I think they're cool. So this isn't a workflow talk, but it's a bunch of different sort of vignettes. And the takeaway message is that so I submitted this talk to the reproducibility track, but that was such a popular track that they actually ran out of space. So that's how come I ended up here. How many of you went to a reproducibility track talk? OK, good. Sweet. OK, so a little bit about me. When this works.
You have to click on Enable Slide Mode on the top right if you want to try and use it.
OK, so I was born in Moscow, and so there's going to be a little bit of like an off-the-grid sort of feel to this, and a kumbaya kind of feel to this, and that you can attribute it to that. I started using Linux about 12, 13 years ago now, so I'm all about free software and open source. And I do have a bachelor's degree in computer science, but don't hold it against me. Here we go. All right, I think my keyboard shortcuts aren't working. I'll just do it this way.
You have to click Enable Slide Mode on the top right, and then they're supposed to work.
So I should really listen to Fernando as the takeaway of the message. Every now and then. OK. All right. So I started off graduate school doing a rotation in a primate electrophysiology lab. And they're collecting data from live brains, primate brains. And this is incredibly difficult data to get. It's extremely rich in terms of what kind of analyses you can do to the afterwards. But you spend several months to years training an animal on a certain task, typically. And then you do something like, minor brain surgery every day, 4 to 6 hours, rather 6 to 10 hours a day for 4 to 6 months collecting that data, right? So this is like real time intensive labor, and people that collect this data typically don't want to give it up. And so I started off as a graduate student thinking, well, if we could just get this data freed, I ended up joining a theoretical lab that doesn't really do experiments. They do computational experiments. And I'm like, if we could just free up this data, if that was just available, if we just shared the data, that would be enough. Like science would progress much better because there wouldn't be this hogging. It wouldn't become this sort of thing that you pass around, or sort of this wouldn't be an arms race. You don't need to stockpile your data. It's something that you share. And so data is very rich. It's hoarded with a very tight lid. I don't know what's going on. OK. So free the data. In reality, having data that's available is not enough. So actually, in the same lab that I ended up joining, theoretical lab, they got a grant to do this CRCNS data sharing initiative, where they compiled data, curated it a little bit from the kinds of this kind of data, primate electrophysiology data, right? This very hard data to get, where typically the culture is not to share data, and it was shared, and they found some hard lessons, like the data is not enough, you need code. Even that is not enough often, right? You have some notes on the data, you have a bunch of README files and things like that. And but I don't mean that, so that's one step to sort of for the progress of science, for reproducibility. You need data, but that's not enough. And so that's all right. All right. So one thing that you definitely do, and I do mean all scientists, right, is that you have to version control everything. And so this presentation's version control, whether or not you use Git is sort of, that's up to you. I think there are good informed opinions about different version control systems. I think that's the easiest way. Like if I were to give advice to a scientist right now, I'd just say just use Git, because especially in our ecosystem, that's just going to be the tool that you use to contribute patches back and things like that. And it's a very powerful tool. But though it is a powerful tool, and we do things like merges and rebases from the command line, it doesn't have to be that way. And so as another sort of little vignette, a friend of mine who's also in graduate school a few years behind me, she's a biologist, and I explained to her what version control is as she was writing some R scripts to do some data analysis. And I'm like, well, let's just sit down, let's just set it up right now. Just on your machine, we'll just get you a GUI version of it and set it up. And it took me about 25 minutes to explain to her what Git was, and I didn't really get into the internals of how it works, but just what she would get out of it, which is that she'll be able to sort of get the diffs between the last time she ran the analysis and decided to push the big save button, and what's changed since then. And so then it took us 5 minutes to set it. So 25 minutes as the pitch and how it sort of works, what the workflow would be like. Then 5 minutes later, installed, and the first thing she says is, I didn't think it would be this easy. Because it really is. Like we think that Git is somehow, because we know all these fancy things how to do in Git, we think that maybe pitching that to a scientist that isn't a super computational person is going to be trouble. But really, there are tools out there. There are Git workflows that are very sort of friendly, and there are Git tools that are better than they were. And they're better than the Git man pages were 4 years ago or whatever, which were just terrible. Okay. So back in the home lab, we do computational experiments and specifically unsupervised learning of natural signals, sort of answering the question of how should the brain encode images given their properties, given the properties of those images. And the very popular data set for this is this Van Hatteren images data set, which was collected in the mid-90s. It's about I think 9 gigabytes of data, of raw images, of calibrated cameras and everything. As of 2007, it had 336 citations on Google Scholar and was the 99th most cited paper in vision literature. Today, that number, I just checked yesterday, that number is up to 802 citations. And then around 2010, there was an email sent to a vision community mailing list saying, hey, does anyone have a copy of the Van Hatteren data set? I've been looking for the 4,000 still images, and here's a link to it, but it's broken. And that link is broken to this day. Because a server went down, and this resource, a resource that has today 802 citations, lived in that one place. And everyone since the mid-90s had been able to hit that website to download those 9 gigabytes, right? And so I would really appreciate your suggestions or help if you have the full database. So I put up a mirror. I did have it on my machine. I just put it up. Shortly thereafter, another graduate student in a sort of a related lab to ours in Germany also put up a mirror. This happened again with another sort of data set that's a less popular data set, but nevertheless, that at that point, I just started sort of habitually downloading data sets and keeping them on disk. Disk is cheap. I have a terabyte drive in my development box, so that's okay. And sort of waiting for something to go down so that I can put it up, right? So that's as a graduate student, by the way, if you have some computational skills or computer hacking skills or ninja skills, you could put those to use and just start doing this, or find something like this in your field, and people will start recognizing your name. You sent this to the mailing list. Like they're not going to care who you are. They're going to care that you provided something for them that they needed, right? So lesson learned is don't take today's data sources for granted. There's actually maybe at the end I'll talk about another thing that's related to this. It's a funny little anecdote. One thing that I haven't had the chance to look into, but we definitely should start looking into, is something called metalinks, which is a way of specifying multiple resources for your the thing that you want downloaded. So whatever it is that some computation or artifact, and you can specify, you know, URLs via HTTP or FTP, or also BitTorrent is something that we should use. Like if a data set is very popular, there's no reason why we should all be hitting that one server and each of us getting our own copy of those bits flowing, right? We can, if it's a popular data set and it's on BitTorrent, then it'll be very quick for everyone to share it, and it'll, the likelihood of it staying alive is sort of increases and goes up. So let's start using metalinks. Let me see quickly, 9 minutes, okay. So data integrity. One way to ensure that the data that you have today matches the data that you had when you originally ran your analysis. So these are for you've done some analysis and you just want to sort of bundle it up, excuse me, and make sure that it's always actually accessing that data, that it hasn't, there's no bit rot involved, like a bit didn't flip somewhere or something like that. And so one way of doing that, just to make this talk a little bit more Pythonic, is to use a decorator that verifies on load, right? This is important. This isn't like, oh, I copied it or I downloaded it or whatever. It's every time you use that data set in your analysis, right? So on load, you can verify with just a little decorator that the data that you just loaded is the same as it was originally when you loaded it. And so I can just show you that really quick. So here's some hashes for some data sets. And here I create a little decorator function that I called with verification that just tries to, based on the name of the data that I'm trying to load, tries to verify that the hash that's up here will be the same as the hash of that actual data once it's been loaded. So there's a verify hash function that's used here to sort of to hash the data, see what it is, and look at the hash that was stored that lives in your code, right? To see that the two are the same, and then the only thing that you've had to add to your code is just a little decorator to that load data routine that you've got there. So that's another little vignette. Okay, but that's also not enough. So because what you want is really data preservation and data conservation and data integrity altogether. And you think to yourself, oh, well, I have some data and a problem. I don't want to lose my data. So you make a copy. So this is data. I don't mean this is in the data set sense where you can put it up on BitTorrent so that other people have it. I mean, this is your own private data right now. You don't want to release it yet. You just don't want to lose it. And so you make a copy, and now you have two problems. You have two problems because should bit rot occur, you don't know which of those two versions to trust, right? And it sort of becomes a nightmare to manage that by hand. And so the thing to do there is to use git-annex. Git-annex is not a tool that's written in Python, but we're not purists, right? We're pragmatists. And I think it's a great tool. It's written in Haskell, and I'll be trying to do a live demo of it. So bear with me, and I do have notes, so that'll be okay. I should mention that before I move on, the data integrity thing, scikit-data does this for some of the data sets, right? It does something like that, this verification of once you've downloaded the data, that it is the same thing that you intended to download, that the download completed properly. All right, so the first thing that we're going to need to do is we're going to need to make some data. So the DUS is data of unusual size. And so here's just some data. So I just created, let's make it a little bit bigger. All right, so I just created some data. Excuse me. All right, so 369 kilobytes of data. I have it here. So what was my step 0 that I skipped?
Version control.
Version control everything. So git init this. Okay, so I'm on the master branch now, and I have data. So the problem is I don't want to add it to my version control. The reason is that now anytime, what if this data ends up being crap? It's going to live, even if I delete it, it's going to live in the Git history. And the typical scientist isn't going to want to do all that voodoo that you can do in order to remove that from the history and rewrite all the commits without some file, right? You can do that in Git, but we don't want the typical scientist to have to do that. So enter git-annex, which is a tool that's built on top of Git, and I'm just going to sort of demonstrate how you would do this with git-annex. So the first thing you need to do is each instance of a Git repo is going to have its own name. So git-annex init, and we're going to give it a name saying this is the original repo. Okay? So I can say git-annex status. And I have an alias for git-annex. It's just called annex. So I'll start using that shortly. Okay. And so what are we going to do? So right now, it just all git-annex knows about is this repo here. And it's called the original repo. And what we do instead of git add, we just do git-annex add. So I'll just say annex add data of big size, data of unusual size, right? Okay. So what's happened here? I just said git-annex add data dus. I'll do an lsl, and you'll see that what data dus became is it became a symbolic link to a really long hash. There's a path to a git-annex directory, but then it's a really long hash after that, right? That's where the actual file got moved to. So what we've done is we've taken a hash of the file. So the contents of the file sort of are encoded in what the file name now becomes. And what git status will now show us is that we've checked into Git a symlink to that file. Does that make sense? So git commit So I have 3 minutes, is that right? Cool. So git commit is, I just checked in this file, but all I've checked in is just this one line, right? There's nothing there. And, but annex knows about the fact that this file lives here, and that way that this file resolves. And I just want to show you real quick before I move on, because the only other thing that I had was I can skip ttyrec, and I'll post my slides. And then I was going to talk about some things about the ipython notebook, but I think, and reproducible research, I think you guys know about this. I think this is cool stuff. Okay, so what I'm going to do right now real quick, just as I go, is I'm going to create a new repo. Suppose that this is a fake USB drive. All right, so I'm going to cd to fake USB, and I'm going to let me do this a different way. Live demos, right? Okay, I'm going to clone this repo to be fake USB. Okay, cd fake, okay, USB. That's fine, whatever. Okay, so in this repo, right, it's still trying to look for that file. You can't see this because of my color scheme, but it's still trying to look for that git-annex folder. And I haven't even initialized git-annex or anything like that, so that's not going to resolve. So what I'm going to do first is, like I told you, git-annex init, and I'm going to give this a unique name. So I'm going to say this is external USB drive. Okay, so I've just defined this, and now I can say annex where is data of unusual size. Well, and it tells me, because git-annex is built on top of Git, it's actually using, if you want to know the internals, it's using a git-annex branch in that Git repo to keep track of where the files actually live. Okay, so it knows that it's in this origin repo, and so then I can just say, oh, annex get data of unusual size, and it just grabbed. What it did is it went up a level and into the repo, like git remote -v. It went to the origin repo, right? It went to this directory and grabbed this file and put it locally, right? And so now I have it here. Okay, and so I've just copied the data, right? I've solved the data duplication problem, right? I can grab things. The verification lives inside this as well, okay? I'm almost out of time. Let me just, live demos, man. How did I run out of time so quickly? All right, so, but basically, the other thing that you can do is you could annex drop things so that it won't let me annex drop from here. So I've dropped it in one place. If I try to drop it from this repo, it's not gonna let me because it needs at least one copy. So it keeps track of multiple copies. And so this is a tool that's built on top of Git. It's super awesome. Let me race through the slides. So ttyrec is another tool that I recommend looking into. It's just a lightweight capture tool for the process that you do in the shell. If you saw the graph term talk, this is very similar, except this is just for yourself and a read-only sort of process of what you actually did. The ipython notebook, it goes without saying what its features are. Whoop. Yes, I will take questions now. Anthony.
So there's nothing conceptually wrong with this like hashing trick, but I found that it doesn't scale very well, even to sort of like moderately sized data, right? If you have like a 4 GB file or data set, the hash just takes forever to compute, and you don't want to take that hit every time you go to do any computation on it in the future. Is there another alternative solution that you thought of?
So the question was, is there an alternative to the hashing trick, because hashing takes a really long time for like a 4 GB data set? I think I haven't thought of an alternative, but you don't have to do this every time. So one of the comments that I want to say is with regards to my original quote of the too long didn't read summary is that, you know, if you care about this, this will be hard, is that you don't have to make everything that you do be reproducible research, right? There's a trade-off. There's some things some really important results, you really want to make sure that you can reproduce them. Your daily analysis, maybe you don't care. Maybe you want to, disable that flag just so you can get some runs in and then later on verify something like that. So I think that, yeah, another one.
Can you comment on the relative benefits of provenance in git-annex versus git-media?
I don't remember much about Git media. I remember looking at it in a while. Do you want to, so the question was, what are the relative drawbacks and differences or advantages of Git media? But the honest answer is I don't remember. I don't know Git media very well, but I'd be happy to talk to you. Yep. I'm sorry?
What kind of analysis do you do on the data you put in the repository? You described at the beginning.
Oh, what kind of data is done on the brain? Yeah. On the brain? Oh,
what kind of analysis? Machine learning?
Yeah, it can be machine learning or sort of system identification to figure out what the neurons that were recorded from, what sort of stimuli they were reacting to.
Did you talk to James Berkeley? He has this,
yeah, I know James. Yeah, similar fields. Yep. Yeah.
He has a repository as well. Are you thinking of putting your data there as well?
So SK data that I mentioned that does this verification. Yeah. I'm aware of it, yes.
Okay.
Thank you so much.
Thank our speaker again.